So in this video, we're going to go through the ratio test for convergence. Now the ratio test is a really useful technique for figuring out when an infinite series is convergent. What's useful about the ratio test is it can be done with pretty much any series. Unlike some other techniques you might have learned already, like alternating series test and geometric series test, you can only use those when your series is in a very specific form. The ratio test can really be done with any series, although it might not always explicitly tell you whether your series is convergent or divergent. And we'll get into that in a second. Before going into this, you should be familiar with how to take the limit of a function. And you should be familiar with what a factorial is. There's some techniques in here that just require you to know some properties of a factorial. I'm going to go through one particular property of it before we start into the examples, but I'm assuming you're already familiar with that concept. So what the ratio test says is, say you have some infinite series, a of n, and we take the limit of this fraction. The limit as n approaches infinity of a of n plus 1 over n in the absolute value. Let's have that set equal to L, whatever that value may be. Then, based on the value of L, the value of this limit, we can determine whether it's convergent or divergent, or there's a specific case where we might not be able to tell anything about it at all. So if L is less than 1, our series is convergent. If L happens to be greater than 1, our series is divergent. And if L equals 1, we're not able to tell whether it's convergent or divergent. We'll need to do a separate test for that. So for this, before we get into the actual examples, let me talk about the factorial thing I was discussing earlier. So we all know, or we should know, that a number factorial, like for example 5, is just 5 times 4 times 3 times 2 times 1. Or another way of writing it is n factorial, where n is some number, should be equal to n times n minus 1 times n minus 2, right? All the way down to, down to times 3 times 2 times 1, right? All the way and terminating at 1. Now, another way to write factorial, right? Here's the general equation I'll give to you first, and then I'll use this example to help describe it a little better. N factorial can be rewritten as n multiplied by n minus 1 factorial. Okay, and this can be more clearly seen with a specific example. I'm going to use 5 factorial for that example. So 5 factorial should be able to be rewritten as, where n is 5 times n minus 1, which in this case is 4, factorial. The reason for that is this part here, right? 5 factorial is 5 times 4 times 3 times 2 times 1. Well, we should already know 4 times 3 times 2 times 1 is 4 factorial, which is how we're determining this. So you're able to separate that front number to get this, and then that'll come up in a future example. So let's actually start getting to the examples. All right. So first we have this here. Infinite series from 1 to infinity, negative 12 to the n in the numerator, and then in the denominator, 5 to the 3n plus 1 times n plus 1. So first thing is to actually just take the limit of that fraction, right? We need the absolute value of n plus 1 over a of n. So this is going to require a little bit of algebra, right? Your algebra skills really need to be sharp in order to do a lot of the more difficult calculus. So we're going to start off with negative 12 to the n plus 1 over 5 to the 3 times n plus 1 times n plus 1 plus 1. And all of this is divided by our normal a of n term, which is just negative 12, n plus 1, or sorry, just n, over 5 to the 3n plus 1 times n plus 1. And there's a simple way to write this, and I typically skip to this next step and skip writing this. I always just take, like, dividing by a number is the same thing as multiplying by its inverse. So what I would typically do is immediately take this and write it in this next form, right? Which is what I'll do with future examples. I just wanted to show you why I'm skipping this portion of it. Right, so I start off with my normal a of n plus 1, 5 to the 3 times n plus 1, multiplied by n plus 1, and then I multiply this whole thing by negative 12n in my denominator, and then my numerator will be 5 to the 3n plus 1, or sorry, not plus 1. Oh no, sorry, yeah, plus 1, and then just n plus 1. Okay, so I'm going to go ahead and simplify some of these. All right, so now I'm left with, I can cross simplify here, right? These two 12 components, because everything's being multiplied. I don't need to look out for anything separated by addition or subtraction signs. And the rule when kind of dividing terms that have like bases and different exponents is to subtract the current exponents. So n plus 1 minus n just gets me positive 1. So here, I'm left with, and I'll just put an equal sign here. What I'm left with is a negative 12 to the first power in my numerator. And my denominator can be cleaned up just a little bit. So this n plus 1 is just going to end up being an n plus 2. This n plus 1 stays as n plus 1. And now I see what I can do with these two components, because they do have the same base. So let's see what their actual numerators are. So I'm going to multiply this 3 out, and this will just become 5 to the 3n plus 3, and then plus the 1 there, so it's going to be plus 4. And the rule is I subtract whatever my current exponents are. Same rule I did with the negative 12s. And what I end up with, so 3n plus 1 minus 3n plus 4 should get me just negative 3. Which means on the bottom I have a 5 to the third power. Taking the absolute value of this, right, because I do have the rest of this here, right? This is in its most simplified form. What I need to then do is change everything so to make sure it's positive. Everything's being multiplied, so I just get rid of the negative sign. And what I'm left with is the limit as n approaches infinity of 12 over 5 to the third. And I'm going to separate out my constant components and my components that contain the variables. times n plus 1 over n plus 2. And I'm going to move this to the front, right? That should be a technique you're familiar with when dealing with limits. And I'm left with just trying to find the limit as n approaches infinity of n plus 1 over n plus 2. When you take the limit of this, you get the limit equals 1. And 1 multiplied by 12 over 5 to the third should then just get you 12 over 5 to the third, which should be 125 as your final answer. So now, based on the rules, we check, all right, 12 to the 5, 12 over 125 is less than 1, meaning this series is convergent. Now, as you noticed, a lot of algebra is involved here. I say it a lot, and I'm sure there are quite a few professors that'll say this a lot, quite a few teachers that'll say this a lot. The hardest part about calculus is the algebra, right? The actual calculus technique was fairly simple, right? The rule for taking the limit of this, very straightforward. And then after that, just check these conditions. Most of the work was done in simplifying this fraction, cutting everything down. So now let's look at our next example. We have the infinite series of n squared over 3n minus 2 factorial. So I'm immediately just going to go into, rather than writing it in this form, I'm just going to go straight into multiplying by the reciprocal, right? So my first component is going to be the n plus 1 component. So I'm going to have n plus 1 squared over 3, and then n plus 1 minus 2 factorial, multiplied by the reciprocal of my original term, right? 3n minus 2 factorial all over n squared. Okay. You could even think of this rule in a different way. Right. Rather than the limit of the absolute value of a of n plus 1 over a of n, you might find it more comfortable thinking about it as this: a of n plus 1 over 1 multiplied by 1 over a of n. Right. However, whatever is easier for you to think of at that point. So now once we have this written out, we can start trying to eliminate terms. All right, sorry about that weird cut. My camera just decided to turn off. So I think we were here just a second ago. So the next portion of this would be to actually cancel out like terms, right, from the numerators and denominator. These two can't cancel out just because they're in different forms. These two might be able to. So I'm going to multiply this 3 out and see what I get. So this is going to turn into 3 times n, which is 3n. 3 times 1, which is 3. Minus 2 should just leave me with a positive 1. Factorial. Now, those look like they can cancel out, right? Because I'm going to use the rule we talked about earlier and change this to a different form. So this is going to change to, right, now I'm dealing with that, 3n plus 1 times 3n factorial, and I'm going to change the 3n factorial to 3n times 3n minus 1 factorial, and I'm going to change the 3n minus 1 to 3n minus 1 times 3n minus 2 factorial, right? And by doing that, I eventually get back to this exact component, and they will cancel each other out. So what I'm left with in my numerator is just an n plus 1 squared. And then in my denominator, I'm left with a 3n plus 1, a 3n, 3n minus 1, and that n squared from the right-hand side. Taking the limit of this as n approaches infinity, we can see that our top term is, like, the highest term is going to be n squared, while in the denominator, our highest term is going to be n to the 2, 3, 4, 5, n to the 5th, right? Meaning that the limit of this as it approaches infinity should just equal 0. And by the ratio test, just have to check whether I'm still recording. By the ratio test, it converges. All right. Now let's look at one last example. Here. So, very simple, short example. N factorial over 6n. Infinite series has 1 to infinity. Okay, so my n plus 1 term is just going to be n plus 1 factorial over 6n plus 1. And my next term, my 1 over a of n term, right, I'm going to multiply it by the inverse of the original, 6n over n factorial. So I'm going to use the same techniques as before, right? Canceling stuff out. I have this 6 that can easily become a, 6 to the n, and a 6 to the n can become just 6 to the first, right? Because of that rule with subtracting exponents with common bases. So my denominator ends up just becoming 6. And then that same factorial rule from before, I can change this to become an n plus 1 multiplied by n factorial, and these two terms will cancel out. So all I'm left with in the numerator is an n plus 1. Now this is a fairly simple thing to take the limit of. The limit of this is just going to be infinity. Right? So this series is divergent. So the main takeaways from this particular test is, ratio test is very useful. You can do it to any series to get, to figure out whether it's convergent or divergent. The only specific case where you just don't know the answer, where it can be either convergent or divergent, is when that limit is equal to 1, right? And that's not uncommon. It can happen. Let me just give you two examples of where you could do that. The limit will equal 1, and it can be convergent, and one example of when it's divergent. So, two pretty simple series. Just gotta think of one. So, infinite series of 1, of just this, right? So, clearly this is going to diverge because the series is 1 plus 1 plus 1 all the way to infinity. However, if you use the ratio test and take the limit of this, it's going to equal 1. So a series like this would diverge. Now, an example where you do the ratio test and the limit's 1 and it converges instead of diverges could be, right, some infinite series of 1 over n to the second, right? So this is actually something we call a p-series. I should have a separate video on that, but basically you can use the p-series test to determine that this is definitely a convergent series. However, using the ratio test on this will get you that the limit of this is going to end up equaling 1. Meaning it's one of those things you don't have, you can't tell whether it's convergent or divergent, right? So the limit equaling 1 when doing the ratio test actually gives you no information to work from. So those are just two examples of kind of why we can't determine anything when our limit equals 1. All right, because they're examples of it converging or diverging under both. Main takeaways from this: your algebra's really got to be like spot on. You should know how to simplify exponents when you have common bases, right? You should know how to multiply common bases with different exponents. You add the exponents. When you're dividing, you subtract. You should know how to work with factorials. You should know how to multiply and do cross simplification for multiplying fractions. But that's pretty much it for the ratio test. Any questions, throw it down in the comments. But other than that, good luck, guys.